both be following up on what Tom said and also on Dara's concluding slide about studying overpopulation on Earth and then using that to understand how we can solve overpopulation on Mars later. Because what I study is software quality, in particular how we can develop techniques and analyses to reason about and measure and then ideally improve that quality automatically. So much of that work actually focuses on developing techniques that can fix bugs in software. So how can we make our software better, minimizing the burden on human developers who are currently faced with this problem. Now I want to start by saying that I'm fundamentally an optimist, which is important because the next slide is sort of a pessimistic slide, and I want to frame this by saying that I think that the human capacity to figure out this new engineering mechanism, that is software, over 60 years, and then use it to build all of the systems that run so much of the world around us, even without AI today, is remarkable. Especially given that it's a disaster. And so even before we get to these systems could turn into Skynet and kill us all, I mean, we need to stop and think about the fact that we already have a problem with software quality. This is a well understood problem. The software crisis was a term coined in 1968 and we have not solved it. Which in the sense that we have just these software systems that are full of more bugs than we could fix if we stopped finding and making new bugs right now and just focused on them. I am an optimist. But I do need to, before I talk a little bit more about the techniques that we've developed to help deal with that problem automatically, and more importantly, what we've learned from those techniques about software systems that humans build that we can hopefully apply to these even more complex systems that we're discussing. I want to give a quick terminology note because I was educated, at least in part, by John at the University of Virginia, and I would be remiss if I didn't say that I'm using the term bug extremely colloquially, which is to say a bug in software, at least in the first part of this talk, is something that the software is doing, likely linked to some mistake in the code made by the programmer. I use the term mistake very loosely, such that the software is doing something we do not want, and we'd rather it do something else. This is the bread and butter of many developers every day. They get bug reports, the software is doing something weird, and they need to fix it. So that gives us the problem statement for much of my work. The point of this talk is not to tell you really how this works. The point of the first part of this talk is to kind of frame the problem space I'm talking about just enough so that I can tell you what we've learned about software and talk about the challenges involved in applying those lessons to AI systems, if it's possible at all. So my problem statement's as follows. We have a program, and it already exists. It's deployed. It's on GitHub. It's the PHP interpreter, which I spent a lot of time looking at. And even the PHP interpreter does an awful lot of things correctly, right? It's a system that people are using. And it's also a system that has mechanisms for detecting problems. This might be some kind of automated analysis, a static analysis or verification engine. It might be a user filing a bug report. It might be a developer implementing a new feature. But it's going to be examining this system and finding problems. Now, as I've suggested, there are many ways you could do this in research practice and the type of work I'm talking about. When I say we've detected a problem, I mean we found some test input on which the program gives us an unexpected test output in a deterministic sense. And when I say that the program is working, I'm saying that it has a bunch of test cases that it's already passing. That's why it's called test case-driven automated program repair. Given that, the goal of this research is to develop magic, signified by the swirly transition, to help find a small, ideally, set of changes, a patch, diff, programmers know what I'm talking about, that when we apply to the input program, makes a very similar program, a very small change, with the important distinction that the negative behavior that we saw before has been replaced with the correct behavior on that input or set of inputs that were bearing witness to it. Now, because of the reality of modern software, which is so typically deployed in these continuous evolution and continuous deployment and continuous feature addition systems, this process, of course, repeats. And I think it's a critical theme of sort of my whole take on software, that I'm not claiming that purple C program is perfect. All I'm claiming is that it's better than red C program. And this process is a continuous cycle. The idea is to reduce the burden on the human developers who have to do this right now such that they can dedicate their brain space to more interesting problems. Now, like I said, I'm not really going to go into the nitty-gritty of what happens in the magic box. That's why it's the magic box. I will suggest a couple of things about it to help inform the later discussion. But I would like to emphasize first that actually, in a very classic sense, we are clients. Us researchers in this space are clients of modern AI and machine learning research. There are techniques that use symbolic reasoning in the very classic sense. There are techniques that use various types of stochastic and deterministic search to traverse the space of possible edits to implement that actual magic. To the best of my knowledge, nobody's thrown anything as complex as a neural network at this yet, but I would be very surprised if it didn't happen within the next 2 to 3 years. The better machine learning gets, the happier I am. The second big takeaway that's important before we get to the rest of the talk is that there is a fair amount of initial evidence that the types of techniques that we've been developing in this space are promising. That they have the capacity to patch bugs in programs that are very large, that are millions of lines of code. They have been demonstrated to patch infinite loops, buffer overruns, vulnerabilities, the works, and even certain security critical defects. There was a really great paper that I had nothing to do with that was published a month ago where they did a really cool synthesized patch for the Heartbleed vulnerability. And so, although I think we have a lot of work to do before we can truly reduce the bug fix burden on developers entirely automatically, we have some reason to believe that we're making correct progress. But that's not really what I want to talk about. What I want to talk about instead is what have we learned about overpopulation on Earth that can help us deal with overpopulation on Mars. That is to say, what have we learned about software and about mistakes in software that we can use to help address mistakes in AI systems? Both those traditional software mistakes, when I have no reason to believe we won't have them in AI systems just as much as we do in everything on GitHub, and the other kinds of mistakes that are unique to AI systems, the incorrect objective functions, and so on. I think, spoiler alert, I think that there are things we can learn, and then there's other domain-specific knowledge from AI that I'm hoping you all can share with me that we will need to fully develop these kinds of techniques to target these systems. But the first question is, well, is this even remotely reasonable? And this is a question I was grappling with as I was working on this presentation, and Bill and I went back and forth, actually. And in the interest of being overly inflammatory, I want to present 2 responses to this question that I believe are overly reductionist, and then reject them. And then hopefully several of you will agree with one or the other, and then we can argue about it at the Natural History Museum. So the first response is that AI systems are insurmountably different from other software, and there's nothing that we can do to take from the kind of applied program analysis that you, Claire Legouis, are doing to apply to them. They're just too different. They're too complicated, they're too opaque, et cetera, et cetera. Now, I reject this, and I reject it in sort of a roundabout way, because the problem with it is that it implies, by sort of unspoken contrast, that the reason that our applied analysis techniques work is that regular software is perhaps not uncomplicated, but not so opaque, clearer in some way. And I said early, I spent a lot of time looking at the PHP interpreter, which is written in C. I don't know how many thousands of lines of code a program needs to be before no single human can understand it, but I will claim strongly that virtually every interesting piece of software has an order of magnitude more thousands of lines of code than that number, which is to say all software is opaque. So maybe AI systems and neural networks are more opaque in some sense, but I need to be convinced that that opacity is of a different variety, since we're already well beyond the bounds of what a single human can understand with any interesting software system. So, and human understanding is kind of my metric, right? And this is one reason I'm an optimist, because we've built all this software together that none of us understand, which I think is a good thing. So the second overly reductionist viewpoint is that an AI system is just another software system, right? And this is the one I tend to when I'm not being careful to scope my claims. Where the claim is, well, software is software, all software is complicated. So we can just do the same thing we did before. I'm going to reject this one too, because I'm trying to be careful to scope my claims in front of you. Because I do think, as we've been discussing over the course of this workshop so far, that there are things about these systems that are different from the software we've been building to date. Otherwise, this workshop would be pointless, right? So by construction, there has to be something interesting about these systems. That means that we should think about how we can develop mechanisms to help them fix themselves. I think that's particularly important because a lot of the success of modern software repair research is predicated on domain knowledge and insights we have about software, the mistakes that happen in it, and how they can be fixed. And in some respects, so we'll have to replace that with domain-specific knowledge about how AI systems are broken and how they should be fixed. So a little bit of column A, a little bit of column B. I think fundamentally, when I thought about it, the challenges for self-repair in AI systems are the same as the challenges for self-repair in all software systems, because I basically fundamentally agree with Tom that we should talk about complex systems and assuring their safety and improving their quality, and that AI is just a feature of those complex systems. But we will have some variety in the solution space. So while I can speak about my expertise about what I'd rather originally called regular software, I'm hoping that the AI and machine learning experts in the crowd will tell me about all the bugs that they run into in their space so we can think about how to fix those automatically. Okay. So sort of unsurprisingly, there are three major challenges for automatic repair of anything. One is scalability, because for any bug, there are trivially an infinity of ways to fix it. It's a very large space. We need to attractively traverse it. Related closely to scalability, and by scalability I mean to large programs and test suites as well, is expressive power, since we want techniques that can scale to bugs that are complex and important and a variety of them. And the third major challenge is how can we be confident that the change that we've made to this system is of high quality? That's actually the hardest part. And it's not unique actually to repair because these systems are ever evolving. So I think it's a particularly important but promising sort of challenge direction for AI systems that are always changing. And so we need to be able to reason about in a principled way how we know those changes are good. And we can learn about the quality of changes by thinking about them for bug repair, but there's nothing special about bug repair in that respect. So I have some bullets where I've reflected on what about regular software makes this tractable, right? What makes program repair tractable in an automated sense for regular software? Focusing first on the expressive power and scalability challenges, I think possibly the most important thing about bugs is that repair can often be conducted via a very small increment over a mostly correct solution, which is to say we're starting with a program that is mostly correct 99 times out of 100. This has there are a couple of reasons behind this, and it has a couple of implications. The first thing is that, the first implication, or I don't know if it's a cause or an implication, is that bug severity has very little relationship to bug fix complexity. Most of the security bugs you hear about hitting the news are the result of somebody forgetting to check that some number was greater than 0 before passing it to malloc. Which, fixing that is easy, right? And we can have a philosophical debate about the true cause of that, right? About the responsibility of between a caller of an interface and the designer of that interface. Is it my fault for calling malloc with a negative number? Is it malloc's fault for not checking? It doesn't matter. Because the point is that fixing a major security vulnerability that results from an underflow is easy. And that means that we can scale to very complex and important problems because the solutions can be done fairly easily, even if the problem is very important. So this is one of those things where I actually am not sure if this is true of failures of AI, and I would like somebody who knows more about it to tell me. The second thing that's good about this is that we can learn about correct behavior from the rest of the system and learn about what the system's supposed to do by the parts of it that we can assume with some confidence are already correct, and use that to inform the kinds of transformations we use to fix bugs. I have no reason to believe that AI is different in this respect. The second important thing that we're leveraging in automatic software repair is that correct versus incorrect program is patterned and repetitive. Human programmers do the right thing 90% of the time, and they screw up on the corner cases. That is 100% true of AI systems too, right? If they haven't learned about, if the system hasn't learned about a particular use case or corner case, it's likely to screw up. This is helpful because it means, again, we can focus on the corner cases, and we can use patterns, things that we know about common fixes to bugs, common fixes to common problems in AI systems, to fix problems that we observe. And we can learn what kinds of symptoms to look for when trying to diagnose a particular error. Most bugs are failure to bounce check. That gives us a really easy way to start trying to fix an automatic problem with a bounce check. The question is, how many cases like that are there in AI systems where we can learn about the common things that people do wrong and the common ways that people fix them? So my question to the AI people then is, what do bugs and bug fixes look like in your world? I'm sort of ignoring the regular code software vulnerabilities here, right? Because the old techniques apply. I'm more interested in the reinforcement learning models, the kinds of mistakes that are unique to AI systems, and how much their features match these features, because these features are what allow us to scale and expressively fix bugs. one more note on this increment thing. What's nice about this increment, the fact that we're reasoning about a change to a program and not the entire program, is that it allows us to scale symbolic and semantic reasoning techniques to very large problems because they scale with the size of the increment and not the size of the program. So I really hope this feature is true of your world because it would make automatic fixing of bugs a lot easier. The much harder problem, of course, is the one I get to when I'm running out of time, is when do we know that a bug is fixed? I started by saying we're going to use test cases as proxies for formal correctness specifications, mostly because we have them. And it turns out that they are not perfect. I really liked this quote, actually, about as soon as a metric turns into an objective, it's now a bad metric. It's completely true in program repair. And what we've seen is overfitting. When you use test cases as the metric for bug fixing systems overfit to the test suite. Now, we have seen that there are some test inputs that are better than others, that some techniques can generalize better for certain kinds of test inputs. And I could speak about that for programs sort of in general, but I don't know how well it translates. But this idea about overfitting, avoiding overfitting as a key metric for repair quality, I think very easily translates to AI systems. But in an ideal world, we have multiple coordinating and multimodal specification and assessment techniques for assessing the quality of a change. I think it was great what Andrew mentioned is that we can use previous models to help us fall back and validate new models, which I think is a feature that's unique to AI and that would really help us in assessing the quality of a change to fix a bug. And I think it's something that humans are already doing. But I do think it's worth mentioning that quality can often be treated as operating on a continuum. So it doesn't matter if the change is perfect or the system is perfect afterwards, so long as it's better. This is sort of me getting up on my pulpit here, so I won't rant about that too much. But I think it's worth mentioning that we need to reason about when perfect correctness is necessary and when something that's just adequate will do. Just to wrap up on this issue of output quality. So as I implied, one way that we literally already measure test-driven repair quality in generic software systems is via generalizability, which is sort of the inverse of overfitting. So any world in which you can help me reason about the degree to which we're overfitting to test inputs is a world in which we can transform software systems that use AI in a way that gives us high confidence. And there is a sense in which AI systems, I think, are particularly well suited to this kind of transformation for repair because so many of them are so highly data-driven. And we've seen empirically in test case-driven program repair that correctness and generalizability of patches produced by these systems is very closely linked to the number of test cases you have and the degree to which they appropriately capture input-output behavior. So having high data volume is good. The more data you have, the better our transformations can be, and we've seen that in practice. But it does tend to renew scalability as a concern. I have 0 minutes left. So what I was going to end on was a picture of my bug again. I won't. Instead, I'll say, I would really like to hear what your bugs are so that we can talk about how you fix them, because I think as soon as we do that, we know, I have some confidence that we can help you fix them automatically.